okay, in this section, we are going to briefly introduce the stability of the negative feedback system. We are going to utilize the phase margin as the indicator to judge the system stability. So we can have the transfer function for Ts, right? So conventionally, we have Ts equals to Ns over ds. N is the numerator, ds is denominator. Both of them are polynomial functions. So conventionally, we can insert this into the closed loop transfer function, which are 1 over 1 plus t and t over 1 plus t. And by reorganizing the polynomial fraction and solve the roots for the pole positions. But that way is kind of too complicated. And alternatively, we can have a relatively simple way to judge the stability directly from the Ts. So we can determine the stability directly from Ts. So now let's see how can we achieve this target. So basically for Ts, we care about the crossover frequency. So suppose the crossover frequency is Fc. So it means that T as S equals to J 2 pi Fc will have its amplitude equals to unity, or we can convert it into decibel scale as 0 dB. This is kind of a definition for crossover frequency. Fc is where the T-body plot hits 0 dB. So at this crossover frequency, we can introduce the phase margin concept. Phase margin is defined as phi m equals to 180 degree plus the phase angle at the magnitude crossover frequency T at J 2 pi Fc. So for the stability of the system, if given two conditions, so condition 1 is that if we have exactly one crossover frequency as Fc for the Ts transfer function. And 2, given the condition that Ts contains no right half plane 0. If those two conditions are true, we can derive that 1 over 1 plus t and t over 1 plus t, both transfer functions for the closed loop, they contain no right half plane pole. Under the condition, right, whenever the phase margin at phi m is positive, so this is the way how we determine the closed loop stability by TS, we can evaluate whether TS contains RHP 0 or not. If TS doesn't have any right-hand plane 0, and there is only one crossover frequency, we can conclude that as long as phi m is positive, the closed loop transfer function have no right-hand plane 0 poles. Then we need to consider how large, right? Now we know that phi m bigger than 0 means stable system. But meanwhile, we need to consider how large phi m are required. So what is the optimal phase margin? So we can consider large phase margin and small phase margin separately. For example, for small phi m, like phi m between 0 and 15 degree or small value. So what does this mean? Right, this means that we have complex poles. Near crossover frequency with high quality factor. So this will bring us overshoot issues in time domain response. And also will incur rainings, right? Not only overshoot, but also rainings in transient response. And what if the phase margin is too large, right? If the phi m is large, large phi m means that we have real poles with low Q. So this can resolve the overshoot problem, of course, no overshoots. However, it also brings drawbacks. Mainly, the response will be too slow, right? Very, very slow. So no overshoots and raining. Of course, no raining. But response time is slow, right? Slow in response. So now let's consider, so those are like literal description. In order to help you to have a vivid understanding about how this description means, we can introduce a numerical example, right? So let's look at an example here. Suppose we have a loop gain transfer function, Ts, equals to like 1 over S over omega 0 times 1 plus S over omega 2. This is a typical loop gain transfer function. So it's like we have a pole at origin, and also we have a left half plane pole at omega 2, right? Based on this Ts, we can derive the expression for T over 1 plus Ts. So this would be equal to 1 over 1 plus 1 over Ts. Then we insert this Ts to here and rearrange the closed loop transfer function for t over 1 plus t. So this will be equals to a quadratic pole response of 1 over 1 plus s over omega 0 plus s squared over omega 0 times omega 2. And we can normalize this quadratic pole response by introducing quality factor and omega c. So this will be equal Ts over 1 plus Ts equal to 1 over 1 plus S over Q omega C plus S over omega C squared. And by comparing the original format and the normalized format, we can easily write the expression for omega C and Q, right? So where omega C equals to square root omega 0 times omega 2. Q equals to omega 0 over omega C, and also equals to square root omega 0 over omega 2. Okay, so based on the closed loop transfer functions, we can solve this transfer function to find out the crossover frequency and to evaluate the phase margin. So we solve for evaluation of the phase margin. So we can get the expression for both quality factor and the phase margin, right? So by analyzing this transfer function, we can solve that the relationship between Q and phase margin can be expressed as square root cosine phi m divided by sinusoidal phi m. And based on this expression, we can plot the curve reflecting relationship between Q and phi m. For this Q and phase margin relationship, we can plot its relationship in a graphical manner, right? So it's like the x-axis is the phase margin, and the y-axis is the quality factor. So here is the origin. For phase margin, we should have it in between 0 degree and 90 degree. So here is the 45. And for quality factor, here is 0 dB. We have 10 dB, 20 dB, and minus 10 dB, minus 20 dB. Based on this formula, we can plot the Q phi m relationship. With the increase of phi m, the Q will decrease. So roughly, it's going to be changing like this. And when the Q equals to 0 dB, the phase margin will be equal roughly to 52 degree. Okay, that is the graphical illustration of Q and phi m. And alternatively, we can also rearrange this expression so we can solve the expression for phi m. So basically, phi m will be equal to arc tangent square root of the fraction with 1 plus square root 1 plus 4q square q to 4 divided by 2Q to 4. So this means that given a quality factor, we can exactly solve the value for the phase margin. Okay. Now let's erase the blackboard. Okay, we have erased the blackboard. Now let's continue to analyze this case study. So we have analyzed the relationship between Q and the phase margin. Now let's consider the time domain response. What if there is a step response, step excitation? So actually we can solve this time domain expression for the output signal. So we would have the output voltage in time domain in such an analytical format. Depending on the value of Q, we'll have two expressions. The first condition is that if Q is higher than 0.5, this means that we would have a pair of complex poles. So in time domain, Vt will be equals to 1 plus fraction of 2Q times exponential of minus omega c t over 2Q divided by 4Q squared minus 1 sinusoidal square root 4Q squared minus 1 divided by 2Q omega c t plus arc tangent square root 4Q squared minus 1. So this is for Q higher than 0.5 case. Namely, there are a pair of complex quadratic poles, right? And for the second scenario, if Q is below 0.5, then this transfer function will contains a pair of real poles, right? So real poles will also have its time domain response for a step change. So Vt will be equal to 1 minus omega 2 divided by omega 2 minus omega 1 times exponential minus omega 1 t minus omega 1 over omega 1 minus omega 2 e2 minus omega 2 t. Okay. Here, omega 1, omega 2 are the pair of real poles. So where omega 1, omega 2 are the pair of real roots for the parabolic equation, right? So which equals to omega c over 2Q times 1 plus minus square root 1 minus 4Q squared. And based on this pair of time domain analytical expression for step change of Vt, we can plot the time domain response for the step change. So x-axis is time, t, origin. Y-axis is step change, Vt. So we consider that the time is from 0 to 15 seconds. So here is 5, 10. And Vt is 0.5, 1, 1.5, 2. For different value of Q, we'll have different shape of profiles. For example, if Q equals to 0.5, which is the boundary, a pair of real poles, right, with same value, then the pole position will just equals Q omega C over 2Q. So we would have such a profile for V small signal T. So this is Q equals to 0.5. And it's like eventually it converges to unity. And for Q below 0.5, lower than 0.5, means that we have a pair of real poles, right? Real poles. So the shape will be lower. So this corresponds to Q equals to 0.2. Remember, for Q is small, right? This means a pair of real poles, right? For too small Q, it means that the phi m is large, right? So you can also read in this curve, small q means large phi m. Large phi m would means that there is no overshoot and raining, however, slow in response. Low Q, large phi m, slow response. No shoot and overshoot and raining, right? And on the other hand, if Q is higher than 0.5, so you will see the curve time response, step response will also change accordingly. So namely, you will have such a profile. So this is a case for Q equals to 1. You can see that there begin to occur rainings, right? Rainings. And also eventually it will converge to stable, right? For even larger Q, you will have such a format. So this is for Q equals to 2, right? So overshoot will appear. So basically, large Q corresponds to this case, right? To this case, a pair of quadratical complex poles, right? So which will means that the sinusoidal part will kind of becoming more and more important. You will see these oscillations which correspond to the raining, right? Correspond to raining. So basically, this means large Q will correspond to small phase margin. And small phase margin will incur overshoot and raining. So to summarize here, we would say that we would like to maintain both good response speed and meanwhile low overshoot or small raining. So usually we would design our system to maintain the phase margin to be in the range of 45 degree to 60 degree. This range is considered to be the optimal range for the phase margin. Okay, so in this section, we have analyzed the stability of negative feedback control, and also combining the specific loop gain, we have quantitatively introduced the relationship between the phase margin and the quality factor. We can see that the phase margin, it is not like the larger the better, and instead we need to consider the practical design specs to optimal design the phase margin. Usually, we consider the phase margin in the range of 45 degree to 60 degree to be the optimal value.